One quick question.
Sure.
Just as far as like notation, we have that.
Forget Preston. All right. So, we're going to do these 4 steps. Step A, show how to determine the interval. So, I guess I should say a little bit about Joe's question. He's like, you know, what if we graphed it on Desmos? Because we did graphing on Desmos a lot. Like even in that problem we just did. I want you to understand something. Where we have been living all semester long has been just on the XY plane, not up here, right? So when I graph solutions, they all live down here somewhere, right? This is our world. The only reason I'm in 3D is because I'm thinking about f of xy for a moment. But the differential equation solution is going to live down on this plane somewhere. So keep that in mind. Okay? So somewhere on this plane we're going to find I initial, I naught. By the way, here's a picture of it, right? It says I here. X minus x naught is less than or equal to h. What's the center of that interval? X naught. See how it's right there in the center? And how far away? Here's x naught plus h, and here's x naught minus h. So hopefully that makes a little sense now, after what we talked about. All right, let's go to the proof. So we want to prove part A, which is show how to determine what the interval is. Part A. Since f is bounded, that was one of the hypotheses, in S. Can I write this, guys, for shorthand? What's that mean? There exists a number m such that, all right, I'm going to use shorthand again just because I want to squeeze it in here. Absolute value of f of x of y is less than capital M for all, or for every point x comma y in S. I'm basically saying what it means to be bounded. It means the value of f can't go to infinity. It's capped by something. What's it capped by? Well, capital M. I'm saying whatever it's capped by, call that capital M. Okay? Do they show capital M here? No, they don't show it. Although capital M is going to show up a few places in a little bit here. But hopefully that's just from our understanding of bounded. Okay, next. We're going to choose H such that the rectangle R defined by, and I'm going to give you a system here of inequalities, 2 inequalities. I want absolute value of x minus x naught to be less than h. Actually, let's make it less than or equal to h. How does that change things? Closed or open. This is a closed interval, right? So on the picture, again from the book, see, x minus x naught is less than or equal to h is on the x-axis. You guys see that? And then the other inequality you can see on the y-axis. We want y minus y naught absolute value to be less than or equal to capital M times h. So we want this rectangle. How do you choose H? You choose H so that this rectangle lies entirely in S. So back to the picture. What page is this? It's, yeah, 735. They say keep referring to it. Look, the X and the Y, right? Now, by the way, how big is M? I have no idea. In this picture, it looks to me like M is about, really about 1. Because it looks to me like H and MH are about the same distance in the picture. It looks like it's kind of a square. You know what I mean? But if your function is really big, maybe M is 1,000, maybe your rectangle would be less than 1,000, but then what you have to do to get it to fit inside of the region S, you would have to make H really small, like maybe 1/1,000,000th or something. But you could do it, right? You can pick some H bigger than 0 to shrink the rectangle enough, whatever M is, to get it to fit inside S. Jimmy, I think you had a question.
Yeah, I mean, it's kind of I know you kind of just said it.
Okay.
What was the shaded region? What is the shaded region with respect to S again?
This is my rectangle R that I'm defining in this very sentence right here. And I'm just making H a small enough fraction or something. It's some H bigger than 0. So actually, I should probably say, choose H bigger than 0, such that the rectangle defined by this lies entirely in S. I can do that because I could make H a really small fraction if I have to. So this is a rectangle, right? Because you have an interval on the x-axis and an interval on the y-axis. They define a rectangle like this. You may have never seen this before, but it works. And then you just shrink it down. You choose H small enough that we want to make sure that, notice the way they did the picture? I mean, it's barely an S. You know what I mean? Oh, where'd it go? Where'd the picture go?
Only one region of it, like it was
Yeah.
that's it.
My goodness. Technical difficulty. So what are the calculations? Well, let me write a few things down. Well, I guess we have everything, right? I mean, I showed you guys all this already, right? Like if you have x minus x not less than or equal to h, you can do this, and then your interval is this. And now I naught, you just take off the endpoints. Okay? So basically, that's the story. How do you find the open interval, right? Part A. Show how to determine the open interval. Well, there's I and I naught, right? So we define, I guess, I to be the interval, I guess, x between x naught plus h and x naught minus h. And that's with less than or equal to. And if I write I0, the open interval, I'm just going to say take off the endpoints. X naught minus h less than x naught plus h. So I have the interval and the open interval. And I am ready now for part B, if you are. Because time flies when you're having fun. What the heck is part B? Part B. Prove that each Picard approximation is continuous and that its graph lies in this rectangle. Now, that's interesting, okay? We're going to now do Picard approximations like we did last week. And we're going to show that each one of them is continuous and lies in this interval we just defined. Okay, Do you guys remember what the first Picard iterate was? The first Picard approximation? So here it is. We look first at the Picard iterate is the word that the book uses. You okay if I use that word? You know what reiterate means?
Restate.
Yeah, let me say it again. No, just kidding. You know what reiterate is? So an iterate is something that you do over and over again. So the first Picard iterate, y0 of x, do you remember what it equaled? This. So it's exactly the same as our initial condition, isn't it? Okay. We see that its graph over the interval I. What's the graph of that look like? I showed it in Desmos last week. Hey, let me get it back. So that's what Joe wanted, so I think I will. I'll show it from Desmos. Here's last week's graph. Which one was the first iterate? Just this thing, right? If I get rid of the other ones, right? The first iterate is just a straight line. Y of x naught is y naught, right? Well, y naught of x, y0 of x. So we see that its graph over the interval I is a straight line through. Do you see that it's through the center of the rectangle? I guess that's the question. Well, let's show the picture again and see if you understand that. Here. Yeah, see this line, x naught? So this is the first Picard iterate. It's going right through there. See that? Because again, x's and y's are kind of flip-flopped here a little bit. Okay. Now, that's the first iterate. Next, we complete the proof of part B, which I'll just indicate this way, by induction. And I'm lucky because didn't I talk about that with you guys already? Proof by induction. You prove infinitely many cases, kind of like dominoes. One case knocks off the next case, which knocks off, right? So we did that. Where did we do that? I'm trying to remember.
In the Laplace transform.
It was the Laplace transforms. Yeah, we proved something by induction. I don't remember what, but it was your first time seeing it. And the thing is, you have to have like one that you know for sure. Guys, what are we trying to prove? We're trying to prove in part B that each approximation is continuous. Oh, a straight line, is that continuous? Yeah. And that its graph lies in the rectangle. And our straight line went right through the middle of the rectangle. Well, now I want to show that when I do the other Picard approximations, this is going to be in my rectangle. This is going to be in my rectangle. All right? This one, this one. What's my rectangle going to look like? I don't know. I mean, it would have to be, here, maybe I'll zoom in. Maybe it would be like a square like here, right? Again, this goes right through the middle of it, but maybe it would be kind of like this. Does that make sense to you guys? The weird thing is, M really depends on the right-hand side of the differential equation, and it's talking about Calc 3. You need a z-axis to figure out what M is. So if you ask me what M is for this problem, I have no idea. I really don't know. I just know it's bounded. What was this equation we did last week? What was the right-hand side? Oh, here it was. X squared plus y is the right-hand side. That's bounded on a region. It doesn't go to infinity unless you go way out to infinity with your inputs. Okay. So we're going to prove by induction. Ready? Here's how this works. Suppose we know that the graph of, now if I write this, y at n minus 1 of x, do you guys know what that means? Suppose I know that the graph of yn minus 1 of x lies in R. This is a Picard iterate like we did last week. If we're trying to do a proof by induction, we must show that this implies I wrote down the same is true for yn of x, that this implies the graph of yn of x also lies in R. That's how induction works, guys. You kind of show that if you get case n minus 1, you're going to get case n as well. All right, so here I go. We know that x comma yn minus 1 of x is in the rectangle. How do I know that? Well, I know that because I just said here, suppose we know that the graph of yn minus 1x lies in the rectangle, right? So I'm supposing this, right? I need to show that yn of x is in the rectangle. Okay, so we know that this is in R, so here we go. The absolute value of f of x comma yn minus 1 of x, that absolute value must be less than m. Can you tell me why? Well?
Is m that mh or?
M is the same m that we're putting next to the h in the rectangle, yes. Where did m first show up? I guess it first showed up in part A. I said, since f is what? Bounded. In S, right? Guys, where does R live? Where does R have to live, we're saying? All within S, so this is true. That's why you need R to be, the rectangle to be in S, so that you can say this. So now what we have is this. We have, let me write it out. Okay, here we go. Absolute value yn of x minus y naught equals, now this is really kind of cool, I think, absolute value integral x naught to x f of t comma yn minus 1 of t dt. And then I'm going to put a less than or equal to here, but I better pause and make sure you understood what I just wrote down. Because I'm not sure. All right. Let's go through this. What is this? Yn of x?
Those are y planes of the rectangle.
It's what I'm trying to show lies in R, yeah. But what is it?
Is that a series of...
It's part of the sequence of functions. Yes, it's part of a sequence of functions. What's the sequence of functions we're talking about today? We're talking about Picard iterates, right? So yn, remember how we got it? Oh, here it is. Here's the formula for it. Look. What does yn equal? Y naught plus, remember this formula? So if you take a look, yn equals y naught plus this stuff. So if I subtract y naught from both sides, yn minus y naught just is this integral. See that? That's how I'm getting this. I'm saying yn minus y naught is that integral. And so absolute value of yn minus y naught equals absolute value of this integral. Okay? Now, there's two more things to write down here. This is less than or equal to the integral from x naught to x of the absolute value of f of t comma yn minus 1 of t. So I guess I have to close a parenthesis there, close another parenthesis, then put dt, and then close the absolute value bars. Okay. So I need to explain. Oh, wait a minute. No, not the bar here. We can actually bring the bar inside the dt. That's the key. I can bring the bar inside the dt. Now wait a minute. Look, guys. See these absolute values? Look right above it. Isn't that the same thing almost? Forget about the integral. See that? What do we know the absolute values is less than? It's less than m. So I can say this is less than integral x naught to x of m dt. Now, there's one thing I have not explained yet, and that's this. How did I get that these absolute value bars of the stuff is less than or equal to stuff of the absolute value bar? Okay? Your book explains it in part B. I don't want to go there. I just want to tell you this is true, and it's very common, and this inequality right here is like the triangle inequality. But I don't know if you guys know that. Do you guys know what the triangle inequality is? I see a no. It's a geometry thing. All right, let me show you what the triangle inequality is, and then we'll come back to the proof. This is good. So here is a picture of a triangle, A, B, C, right? So the triangle inequality says AC is less than, by the way, do you know what when I write AC, do you know what I mean?
Segment between the
Yeah, the length of that segment is less than AB plus what?
C.
Yeah. You know how you learn the shortest distance between 2 points is a straight line? That's really the triangle inequality, it's sometimes called. It says you have less than, right? Now, it's funny because I guess what we're doing is less than or equal to. Now, it's not going to be equal to unless B is on line AC, right? You guys with me on that? That is what I just did here. Really? Well, kind of, because here we're adding. And we're talking about distances. Distances are represented by absolute values, right? If you want to add up infinitely many distances, you integrate those distances, and that's the same as the sum. So like the right-hand side is a sum of distances, so is this. It's just infinitely many of them. Oh, I'm pointing to nothing. Well, thank you. Try it again. The right-hand side is like this, the AB plus the BC. It's infinitely many distances added together, integrated. And then the left-hand side is just kind of going straight there. Take the distance of the one integral. All right, so if you buy that, then I think we actually proved this line. So what were we trying to prove in part B? Oh, gotta keep going back. Oh yeah. Prove that each Picard approximation is continuous and that its graph lies in the rectangle. We know the first one does. We're assuming the n minus 1 does. And we're trying to show that the nth one does. Well, let's see what we have. All this is showing me that the absolute value of yn of x minus y naught is strictly less than, by the way, if you integrated this, what would you get? Well, first of all, m is a constant, right? Let's take that out. M. If you integrated dt, what would you get?
MT.
Yeah, it would be t, but then you have to plug in what? Your x and your x naught, right? So you would get x minus x naught here. Right? Now we just showed that yn minus y naught is less than m times x minus x naught. Okay? And I guess that's what we wanted. Because doesn't that show that we're in the rectangle? Wait a minute. How did we define the rectangle? The rectangle was defined, x minus x naught is less than or equal to h, y minus y naught is less than or equal to mh. So if your h here, yeah, right? X minus x naught is less than or equal to h, so this is less than or equal to m times h. So we got it. We actually just showed that the yn, right? We must show that this implies the graph of yn also lies in R, and I'm going to say we did part B. We did it. And I'm going to pause it right here. So, look, here's proof of D, right? D is all about what again? Do you remember? Yeah, we got uniqueness. So C is proving existence. All right? Parts A and B were kind of like setting up for part C. Okay? So we're ready now to prove existence of a solution somewhere in the rectangle. That's kind of how this works. Now look. It says that here's the closing of part C. We have thus proved the existence of I naught of a particular solution of 58.53 satisfying 58.54. What that means is of, here I'll show you guys so you can see. They're saying a solution of this satisfying that. That's what they're getting. Okay? How do they do it? They use Picard iterates, right? Isn't this a Picard iterate here? Well, this is maybe a limit, right? Because you see the x naughts in both places. So you just get y naught. All right, but what the heck are we doing in the 4 pages in between? It's a lot. So let's go back to the beginning and see kind of how do they start to prove this? They say by the second equation and by a certain theorem, we can write this inequality. Is it worth writing that down? Probably not with 3 minutes. When I did it last time, here's what I did. Yeah, we're not going to write any more down, guys. We'll just kind of watch. Okay. y1 minus y0. This is only looking at the first 2 Picard iterates. So on the picture, guys, get rid of these. We're only looking at the blue one, which is a cubic, and the red one. And it says, let's compare them. Let's measure the distance between y1 and y0. Well, that equals this. Why does it equal this? Again, because remember when you compute y1, there's a y naught on the other side. Remember that? So we've done that before. And we just showed that's less than or equal to m times the matter of fact, didn't we do all this already? Yeah, we did all this already. So we got y1 minus y0 is less than or equal to mh. Now, the next step, you look at y2 minus y1. They use that inequality again and bring the absolute value inside. They say for all x in I in the interval, these 2 points are in R. Now, how do we know that? It says y1 and y2 are both in R. Well, because they're both y values. And therefore, you can say it's less than or equal to n times something. That's crazy. Crazy, crazy. Yeah, I don't... Unless you could see it from the picture, I'm not going to have enough time. So let's take a peek at the picture. And then just... Oh, I lost the picture because I went back. Here it is. Yeah, we're going to stop. We're going to say, guys, we didn't get to part C very far. That's okay. I think you saw some things about proof and got our hands dirty enough that I say maybe we appreciate existence uniqueness more than we do.
So when you're measuring the distance between like the 2 functions,